Today I'm going to talk about Drake's equation, which was a way scientists estimate how many detectable intelligent civilizations might exist in our galaxy. The equation was created in 1961 by astronomer Frank Drake. He wasn't trying to give an exact answer, but instead break down a huge question into smaller scientific pieces. Each part of the equation represents a step needed for intelligent life to exist and be detectable, from stars forming to planets forming to life, intelligence, and technology. What makes Drake's equation interesting is that it mixes known science, like star formations, with big unknowns, like how often intelligence evolves. Depending on the values you choose, the answer can change a lot, which is why the equation is still discussed today. The first part of the equation is R star, which is the rate of star formation in the Milky Way. Based on modern observations, astronomers estimate that our galaxy forms about 1.5 new stars per year. Many of these stars form in clusters surrounded by disks of gas and dust where planetary systems can begin to form. This number tells us how many chances per year the galaxy gets to potentially create planets and eventually life. Next is the fraction of stars that have planets. Thanks to the Kepler Space Telescope, we now know that planetary systems are extremely common. Kepler showed that nearly every star has at least one planet, so for this value, I used 1, meaning 100%. This was a huge discovery because before Kepler, scientists weren't sure how common planets really were. Now we know planets are basically a rule and not an exception. NE represents the number of potentially habitable planets per star system. Studies suggest that about 10 to 30% of Sun-like stars have an Earth-sized planet in the habitable zone, which liquid water could exist. Liquid water is important because all life we know depends on it. I chose 0.2 right in the middle of that range, keeping the estimate realistic without being overly optimistic. Now we move on to more uncertain territory. This value estimates the fraction of habitable planets that actually develop life. On Earth, life appeared relatively quickly once conditions stabilized within a few 100 million years. However, Earth is our only example, so we can't be sure how common this really is. Because of that uncertainty, I chose 0.5 or a 50-50 chance as a balanced optimistic estimate. This value represents the fraction of life-bearing planets where intelligent life evolves. While simple life might be common, intelligent life is much rarer. On Earth, it took billions of years and countless evolutionary steps for intelligent beings to appear. Because intelligence requires very specific conditions and long-term stability, I used a small value of 0.005, meaning only 0.5% of life-bearing planets will develop intelligent life. Even if intelligent life exists, that doesn't mean we can always detect it. This value estimates the fraction of intelligent civilizations that develop detectable technology like radio signals. Some civilizations may never invent radio, may stop broadcasting, or use technologies we can't detect. I chose 0.0005, meaning only a tiny fraction of intelligent civilizations ever become detectable to us. L is often considered the most sensitive and dramatic part of Drake's equation. L represents how long a civilization releases detectable signals into space. Civilizations may destroy themselves, change technology, or stop broadcasting altogether. I chose 55 years, which is roughly how long humanity has been producing strong radio signals so far. This shows how fragile and temporary detective civilizations might be, and how much this one number can cause the entire equation to collapse. At this point, we can look back at the full Drake's equation. Each term represents a filter. Stars form, planets form, some planets are habitable, some develop life, some develop intelligence, some develop technology, and only a few will last long enough for us to be able to detect them. Even small changes to one value dramatically affect the final result. Here's the equation with all of my chosen values plugged in. Most of the numbers start off fairly large, but as soon as intelligence, technology, and longevity are included, the estimate drops sharply. This shows how rare detectable civilizations might be, even if life itself is common. When all values are multiplied together, the final result comes out to be 0.00002 20625 detectable civilizations per galaxy. That comes out to approximately one detectable intelligent civilization for every 48,485 galaxies. This doesn't mean intelligent life doesn't exist, but instead shows how unlikely it is for civilizations to overlap in time and technology. Drake's equation reminds us that the universe may still be full of life and still feel very quiet. For the values in this equation, I relied on a mix of historical and modern scientific sources. I used Frank Drake's original 1961 paper to explain the purpose and background of the equation itself. For planet-related values like how common planets are and how many might be habitable, I used data from NASA's Kepler mission and a peer-reviewed study by Pettigura and colleagues. These sources support the earlier parts of the equation with real observations, while the later values like intelligence and detectable technology are much more uncertain and meant to show how assumptions dramatically affect the final result.